Good morning students. Today we are going to discuss few important topics from the chapter 3 current electricity. The first topic which we are going to discuss is your electric energy. Now what is electric energy? Let me try to define by the statement. The work done by source to maintain a current in an electric circuit is known as electric energy. Now the expression can be defined as we have given. Number one, from the definition of the potential, that is your V equal to W by Q. Potential is your work done per unit charge. So work done comes out to be your VQ. Now number two, V equal to IR, it is from Ohm's law. Now Ohm's law states that potential is proportional to current under constant temperature, that is V equal to IR, and R is the resistance which is constant. And number three, already we have defined current, the amount of charge that flows through a particular area of cross section in unit time constitute electric current. So using 2 and 3 in 1, so W equal to VQ, in place of V you can substitute IR, and in place of Q you can substitute IT. So the final expression comes out to be your W equal to I square RT. This work done is nothing but some kind of heat, because when current flows, heat develops. So you can say the amount of heat develops is nothing but I square RT, and that is equivalent to the work done. And work done, as per the definition, the work done by a source to maintain a current in an electric circuit is known as electric energy. So this is one important topic. Now next one which you are going to discuss is your electric power. Now all of you know power is nothing but is your rate of doing work. So as per the definition in electricity part, same expression we are going to use to define electric power. So electric power is defined as the heat energy produced per unit time in an electric device. So electric power, P equal to electric energy by time. So electric energy already we have defined in terms of work done, that is your I square RT. So I square RT divided by T. So TT goes off, you will get power equal to I square R. So these expressions are very important for the numericals. I think most of you know some expression because we have got some expression in lower class. Now next topic which we are going to discuss is your combination of resistors. Probably you have done this topic also. So two combination we will consider. One is your series, another one is your parallel. So two resistors we have considered, R1 and R2, and connected in series. In series basically one terminal is common for both the resistor. A source is connected whose potential is your V, and a key is there, and we are going to denote that key by K. Now positive terminal, so the current flows from positive terminal and it moves through the resistor R1 and R2, and again it moves to the source. So definitely as current is flowing through a resistor R1 and R2, so you will get potential across R1 and R2. Okay, you will get potential across R1 and R2. So total potential is nothing but the sum of the potential of the resistors. So as we have connected two resistors here, so V equal to V1 plus V2. So whenever you draw the circuit diagram, don't forget to give the dot. Dot basically symbolize that circuit is closed. Now V equal to V1 plus V2 as per the conservation. So V1 equal to I R1, because same current is flowing in R1 and R2. So V2 equal to I R2. So I cannot be common. So within the bracket you will get R1 plus R2. So V by I equal to R1 plus R2. Now V by I is nothing but is your R, and R is your equivalent resistance. So in series the equivalent resistance is nothing but the sum of the resistance of the resistors. Now in parallel combination, what we'll do, we again we are connected two resistor R1 and R2 in parallel. So in parallel basically two terminals are common. So a source is connected whose potential is your V and a key is there. So definitely you must have to close the key by giving one dot. So when you close the key, what will happen? Current flows, and current will split up at the junction. I1 is the current flowing through R1 and R2 is the current flowing through R2. So again they combine at the junction after passing through R1 and R2. So again I moves, current I moves. So as per the circuit diagram, I equal to I1 plus I2. So as potential is common for both the resistor R1 and R2, so again you are going to apply Ohm's law. So I1 can be replaced by V by R1 and I2 can be replaced by V by R2. So if you take V common, then within the bracket you will get 1 by R1 plus 1 by R2. Now V you can take it out on one side, that is your I by V. So I by V is your 1 by R1 plus 1 by R2. So I by V basically it's your 1 by R, and R is your equivalent resistance. So in parallel 1 by R equal to 1 by R1 plus 1 by R2. So in numerical it is also used to come, but few things we have to keep it in mind. In series basically one terminal is common between two resistors, and in parallel two terminals are common for two resistors connected in parallel. And in series potential is equal to the sum of the potential across the resistor. If two resistors are connected in series, then potential will be the sum of the potential across the resistor. If it is three resistors, then three terms will come, V equal to V1 plus V2 plus V3. So as the number of resistor increases, so number of terms also increases. So in series, potential equal to the sum of the individual potential across the resistor, total potential. And in case of parallel, current is equal to the sum of the current that flows through each of the resistor. So these two things you have to keep it in mind because numericals are there and you have to apply this formula. Probably you have got these two topics in class 10, so we are repeating here once again. Now next topic which we are going to define, cells, EMF and internal resistance. So most of you I think hear the word cell. So what is cell? Let me try to define. A cell is a device which provides the necessary potential difference to an electric circuit to maintain a continuous flow of current in it. So definitely if you want to let the current flow in a circuit, definitely you have to provide a cell in the circuit. So cell basically denoted by one positive terminal and another negative terminal. So longer one is your positive and smaller one is your negative. So a cell is a device which provides the necessary potential difference to an electric circuit to maintain a continuous flow of current in it. Now next is your EMF. So EMF of a cell may be defined as the potential difference between the terminals of the cell when no current is drawn from the cell. So you see EMF is the maximum value of potential, you can say, okay, because no energy is drawn from the cell. When no energy is drawn from the cell, then the potential difference of the cell is nothing but its EMF. But as the energy starts flowing from the cell, so it is no longer EMF, rather it is terminal potential difference. So this part we will use later on in our coming topic to derive the expression. So you can say EMF is the maximum value of terminal potential difference. Now internal resistance of a cell is defined as resistance is nothing but some kind of opposing force. So here is also Internal resistance of a cell is defined as the opposition offered. I'm repeating once again. Internal resistance of a cell is defined as the opposition offered by the electrolyte and electrodes of the cell to the flow of current through it. So if you consider a cell, what are the things there inside the cell? Electrolyte and electrode. So the opposition offered electrolyte and electrode can be defined as internal resistance, because internal means it is inside the cell, no? So inside electrolyte and electrodes are there. So the opposing force provided by these two components can be defined as internal resistance of the cell. Now the next topic which we are going to define, that is nothing but is your note. You have n identical resistors and you are going to connect one time in series, another time in parallel. So what will be the equivalent resistors? That part we are going to define. So for n resistors identical connected in number 1 series, equivalent resistance will be what? R equal to NR. So it is n times that of the value of the resistance of individual resistor, the equivalent resistance. And in parallel combination, 1 by R equal to n by small r. So R is connected, R smaller resistance connected in n value, means n set of resistors, and each of resistor has its resistance smaller connected in parallel. So equivalent resistance will be your 1 by R equal to small n by small r. So capital R equal to R by n. So you have seen that in parallel equivalent resistance decreases, whether in series the equivalent resistance increases. So this is all about your few topics that we are going to that we have discussed in this class. So more we will discuss next class. But one thing I want to keep in your mind, please download the videos during very day of the class, because I don't have enough space in my mobile, so I can't store all the videos. Okay, so do this thing please. Thank you.